This experiment begins to look at the properties of acids and bases and the reaction between an acid and a base. While an acid is a compound that can give up a proton, so an H+ ion, a base is something that can take in an H+ ion. The most basic acid-base reaction, or the most fundamental acid-base reaction, is that of H+, the acid ion, and hydroxide, OH-. This is the basis for almost all acid-base reactions, looking at the pure acid of H+, reacting with the base of OH- to form an equilibrium with water. And this experiment begins to look at that reaction in the form of a titration.
This experiment focuses on the introduction of acid-base reactions, as well as starting off with the pH scale, which is a measurement of acidity. Acid-base reactions are equilibrium reactions that are occurring with the H+ proton and the OH- hydroxide anion. The primary reaction for all acid-base reactions is this: the proton reacting with a hydroxide to form water. Many things will have a level of acidity to them. Lots of different aqueous reactions and even water itself. All of them have some level of acid present in the system. And this is because of the equilibrium of this reaction in water itself. The Kw, or the equilibrium constant of water, is shown where you can see there is at all times a some concentration of H+ and some concentration of hydroxide present during all of these reactions. The pH scale is a measurement scale used to measure the level of acidity within a solution. The pH of a solution is the negative log of the concentration of H+. You can also have terms like the POH, which would be the negative log of the concentration of OH-. It's a logarithmic scale, which typically ranges from 0 to 14. This is the 14 limit is based on the pKa, or I'm sorry, the Kw of water. While this is the typical range, ranging from 0 to 14, there can be acids that have a lower pH than 0. And this is all based on concentration. The pH scale is a concentration scale, which can be seen here. If you have a concentration of 10 molar, then the pH of the solution would be -1. If by chance you were able to have a concentration of 100 molar, the pH would be -2. Concentrated hydrochloric acid has a concentration of 12 molar and therefore would display a negative pH. Pure water is based or has a pH of 7. This is considered neutral. Things that have a lower pH than 7 are acidic, and things that have a higher pH than 7 are basic, because the concentration of H+ is very low.
The reaction itself uses a burette, which is a device that can very accurately add specific volumes, and you can measure the exact amount of a volume that you add. Doing so is a titration. Now, This reaction and the one in the simulation, as well as many others, use indicators to visually show when a reaction is complete or not. The indicator used in the simulation and in many times this titration is phenolphthalein. But there are a number of different indicators that can change color depending on the pH. Universal indicator is a blend of a few different indicator solutions in order to cover a full range of pH or acid concentrations. These four solutions are all just tap water. They all have a relatively neutral pH and the color is green. However, if I add a small amount of hydrochloric acid, the solution will turn red. Or if I add a small amount of base, the solution will turn a purple color. Depending on the different colors and different combinations of acids and bases, the universal indicator can have a range between an intense purple, a blue, green, yellow, orange, or red color. That's because of the different indicators that are changing color because of the chemistry of the pH.
This experiment also introduces you to the concept of titrations. A titration is the very careful and precise addition of one compound to another in order to perform the reaction very quantitatively, where you can figure out exactly the ratios between reactants where the reaction is complete. Using a burette, you can see these titrations and measure these volumes very precisely. Burettes are meant to deliver an exact volume, not to contain it. A 50 milliliter burette can hold more than 50 milliliters, but the burette itself is used to measure how much is removed from the burette and added to the flask or container below. When you're going through a titration, typically there is some sort of an indicator or a chemical that is added where you can see whether the reaction has run to completion or not. As you're slowly adding the material from the burette and adding it to the material in the flask, the indicator will change color. When you see the slightest variation in color, this is where the exact point of the reaction is finished. This is where the ratios between the compound or reactant in the burette and in the flask are exact. Not necessarily 1-to-1, but whatever the stoichiometric ratio between the two happens to be. If the color becomes very intense, this is an indication that it's over-titrated. There has been too much from the burette that is added, meaning the color is very, very dark. If there's no color at all, that means it's under-titrated and you need to add a little more. When something is under-titrated, this is easy to correct just by adding more liquid from the burette. But if it's over-titrated, this generally means that you would have to start over and repeat the experiment. Indicators themselves are chemicals that display different colors depending on the different conditions that they happen to be in. So they're different environments. There are many different indicators that change color based on the level of pH or the level of H+ that is present in the solution. The indicator that you're working with in this experiment is phenolphthalein, which at lower pH is colorless, and at higher pH, the chemical structure rearranges and becomes a pink or fuchsia colored solution. At this point, when there is a higher pH and the solution turns pink, that's an indication that all of the H+ is used up and the sodium hydroxide, which is in the burette, is changing the pH to a basic pH, a high pH, causing the color to change in the flask. The experiment itself is looking at the standardization of sodium hydroxide. You're standardizing a compound to get a precise and exact measurement of the concentration. The stock solution that you're working with is 1 molar, and that is the only level of significance that it has, a 1-digit level of significance, only one significant figure. But when you standardize this through the chemical reaction, you're using more precise volumes and more precise measurements of the other component. And then through the chemistry, you can get an exact concentration out to a higher level of significance. Laboratory settings use this a lot when you're preparing a solution and you need to know exactly what is the concentration, not just an approximation, but an exact concentration that you would be using out to a much higher level of significance and a much higher precision. The experiment itself is a virtual experiment, which is performed at the Chem Collective site shown here.
The reaction in the lab is the reaction of potassium hydrogen phthalate, which is an acid, with sodium hydroxide. The sodium hydroxide is in the burette, while the potassium hydrogen phthalate is in the flask containing the indicator of phenolphthalein. In acidic conditions, the phenolphthalein is colorless. However, upon addition of base, a pink color begins to emerge. When performing titrations, you need to make sure that you're recording the total volume that is added to the flask. So you need to make sure to record the initial volume reading of the burette and the final volume reading of the burette. The difference between those volume readings is the volume that was added to the flask. Many times it may be very helpful to use a white background to look at the slight color changes that are occurring as the titration progresses. In a lab titration, the color change needs to be maintained, and typically for at least a minute or so before it would be considered the titration is complete. You can see the light color change of light pink, indicating that the titration has been completed. You're going to perform a number of different titrations and look at the volume it takes of sodium hydroxide based on the number of moles of potassium hydrogen phthalate. Using the moles of potassium hydrogen phthalate and the volume of your sodium hydroxide, you can obtain a molarity of your sodium hydroxide solution.
When you first start the virtual lab, the first thing you will need to do is prepare your solution. For this, you will need distilled water, and additionally from the stockroom, you will need an approximate 1 molar solution of sodium hydroxide, and in glassware, you will need a 250 milliliter volumetric flask and a disposable pipette. The first thing you will do is calculate, based on 1 molar sodium hydroxide solution, what volume would be needed for you to prepare 250 milliliters of your desired concentration. You are choosing between a concentration of 0.3, 0.4, 0.6, and 0.7 molar. I'll be showing you the preparation of a 0.5 molar solution. You can drag the 1 molar solution to the volumetric flask and add the desired amount. The flask now contains exactly 125 milliliters of approximate 1 molar solution of sodium hydroxide. When I dilute this, I will need approximately 125 milliliters of water to bring it up to the final volume of 250 milliliters. I am not filling it all the way to the exact amount by pouring it directly from the water flask into the volumetric flask. Instead, I will use a disposable pipette to add in the remaining amount. In this way, the exact amount in the volumetric flask is shown. Notice the volume in the volumetric flask is now appearing in the neck. You want to add the amount of water until this point reaches the exact 250 milliliter mark. Once the solution is prepared, you can take this and use it in the next step, which is a titration with potassium hydrogen phthalate. The remaining pieces on the lab benchtop can be removed to remove the additional clutter. In the second part of the experiment, you are using the solution that you prepared in the first part and performing a titration with potassium hydrogen phthalate. The indicator is phenolphthalein, which you can add 1 milliliter to the potassium hydrogen phthalate solution. You will also need a burette, which is listed under Other. If it says that the workbench is full, many times it is because there is something in the way of where it's trying to add the burette. You can then take your sodium hydroxide solution and add this to the burette. This is a 50 milliliter burette, but if I add exactly 50 milliliters, it only brings it up to the 2 milliliter mark and not the 0 mark. This is because burettes are designed to add, to measure exactly what is poured out from the burette, not what is contained inside. I can add an additional 2 milliliters, and that brings the burette exactly to the 0 mark. The next step would be taking the burette and realistically dispensing it into the potassium hydrogen phthalate solution until the color of the solution in the flask changes to a pink color. Since you will know the approximate amount that should be needed, you can add quickly until a point and then start to add more slowly. When the solution changes color, this is an indication that all of the potassium hydrogen phthalate has been reacted with sodium hydroxide. The exact amount of sodium hydroxide that it reacted with can be based on the moles, which is coming from the potassium hydrogen phthalate solution, and the volume of the solution, which is coming from the burette. Based on these two numbers, you can determine the molarity of your solution in the volumetric flask. The moles are being calculated from the KHP because it is a 1-to-1 ratio, and the volume is being determined from the burette. So in this reaction, you're reacting the KHP, or potassium hydrogen phthalate, with sodium hydroxide. The acid part, or the acidic region of this compound, is shown here. A carbon atom at the vertex with a double bonded oxygen and a single bonded OH group. This is a carboxylic acid. And these are very important when you move on to organic chemistry, as they can be the basis for a lot of different reactions. The hydrogen on this OH group has its electron drawn more towards this oxygen and is able to leave relatively easily. This is because there's a high region of electronegativity. You have this oxygen here with 2 lone pairs of electrons, and this oxygen here with 2 lone pairs of electrons. All of them are kind of pulling that one lone electron from the bond towards these oxygens, so the hydrogen can easily leave. That's the whole basis and reactivity of carboxylic acids, is that this hydrogen can relatively easily fall off. In the reaction, this hydrogen, which falls off, reacts with the sodium hydroxide or the hydroxide group to form water. The result of this is the phthalate ion, which is shown here, where you have these two regions of carboxylate areas. Overall, the net ionic reaction is just the H+ reacting with the OH- to form water, the basis of an acid-base reaction. If you have something that has more than one H+ or more than one hydrogen, this is a polyprotic acid, or something that has more than one proton that can react with hydroxide. In this case, this is phthalic acid, and now it has two of these carboxylic acid regions. So there are two hydrogens that can break off and react with sodium hydroxide. Overall, it will still end up with that same phthalate ion. The reaction itself is still H+ plus OH- in an equilibrium with water, but in this particular case, you would need twice as much sodium hydroxide to react with it, because for every one molecule of this phthalic acid, it will take 2 molecules or 2 moles of sodium hydroxide to react. There are 2 hydrogens, meaning it takes 2 hydroxides. Many of the acids that you're working with might be monoprotic or just have one hydrogen on them: hydrochloric acid, nitric acid, or acetic acid. But you'll also see diprotic acids, or acids that have more than one proton, like sulfuric acid, which is H2SO4, carbonic acid, and more carboxylic acids like this phthalic acid here or oxalic acid. You may even see triprotic acids such as phosphoric acid, which has 3 hydrogens for every 1 acid molecule. Overall, in the report, the calculations are fairly straightforward. In the first part of the reaction, or the first part of the experiment, you're preparing a solution from an approximate volume. And to get that, to obtain the volumes needed in the simulation, you're using the dilution calculation, the M1V1. So you have the stock solution of 1 molar, and you're trying to figure out the volume of that you need. And that's M1 and V1. M2 is the molarity that you're choosing to prepare. In the procedure, this is listed as 0.3, 0.4, 0.6, or 0.7 molar, all out to 3 significant figures, so 3 decimal places. So once you have that, and the final volume of your solution is the 250 milliliter volumetric flask, which has a significance of out to 2 decimal places. So overall, when you calculate your solution, you'll be getting 3 significant figures at the end. Once you have your solution prepared, the next calculation is in determining the actual molarity of your sodium hydroxide solution. So molarity is moles over liters. The moles are coming from the moles of the potassium hydrogen phthalate. Each of your trials contains exactly 25.00 milliliters of the KHP at a concentration of 0.500 molar. this reacts with sodium hydroxide in a 1-to-1 ratio. So by using these this volume and this molarity, you can figure out how many moles of potassium hydrogen phthalate are in each flask, and therefore how many moles of sodium hydroxide would react with it. The volume that you are using is coming from the burette itself. The volume it takes to react with this number of moles. So when you have the number of moles coming from the KHP, that's the same as the number of moles of sodium hydroxide that will react. So you have moles, and the volume, or the liters, will be the volume from the burette itself. Now in burettes, many times you may start exactly at 0, but you don't always have to. The volume delivered from the burette would be the final reading minus the initial reading. And all of these burettes, both in the simulation and in real lab settings, can be read to 2 decimal places. You can read between the lines to get another level of significance. Overall, the concentration of sodium hydroxide that you calculate based on your standardization should have 3 significant figures.
In this experiment, you're preparing a solution in a volumetric flask and then standardizing it through a chemical reaction. The prepared solution would only be known out to 1 significant figure because the stock solution it started with is only known to 1 significant figure. However, by using a titration and knowing the moles and volume out to a much more out to a higher level of precision, to more significant figures, the resulting molarity can be determined out to 3 significant figures. In this way, you can take something that is just very generally known and get a very precise and very accurate measurement on concentration. And by doing so with this titration, you're able to look at the starting reactions of an acid and a base.